Okay, welcome to class, everybody. We're going to pick up where we left off last time, which was just at the beginning of chapter 5. But before we do so, I want to start out with just a little bit of context for why you might care about this. So one of the things that I mentioned before I sort of described this, I want to show it to you briefly. When we talked about crystalline versus amorphous materials, a crystalline and an amorphous material might both be completely solid, right, not liquid, and yet they can have really radically different properties because in one case, the atoms are arranged in some sort of long-range order, right? Like an FCC lattice or a BCC lattice. But in another case, it's just a jumble of atoms, right? And I mentioned that you can actually do this in metals, right? It's hard, and it's only been in the last couple decades that we've figured out how to make amorphous metals. But take a look at the properties, right? I've got two ball bearings here, and I've got two sort of steel plates, right? So it's a little block of steel. They're essentially the same, except that one of them has a thin coating on the top, about 2 millimeters thick, of amorphous metal, right? And if I take these things, and I think I mentioned what would happen in class, but if you take these and drop them from the same height at the top of these two pillars, if you can kind of see this, the regular metal has stopped already, and this thing's still like half the height and bouncing, right? So pretty incredible. If you zoom in and were to look at this, I understand it's going to be hard to see, but if you look at the surface of this, Hector, what do you see? It's rough. Yeah, it's rough. It's got kind of like freckles or little pock marks on it. So what's happening is that every time you take one of these ball bearings and drop it, you're denting the surface of that, because metals dent, right? They're not the hardest things. I mean, some are harder than others, but they can be dented. And the reason they can be dented so easily is because you have a nice arrangement of atoms, right? If you look at sort of like the squares in this, right? If I was trying to slide atoms past each other, because they're nice and arranged, I could slide this row of atoms past the other ones. But if it was a jumble and they're every which way, as I tried to slide it, it's going to bonk into another one. And so amorphous materials that don't have structure tend to be much, much harder. And if they can't be dented, right? If you look at this one, it's basically mirror finish. It's much, much smoother than the other. If you can't dent the metal, then you can't absorb energy. If you don't absorb energy, we don't just delete energy. It has to get transformed back into kinetic energy, so it bounces back up high again, right? So it makes for a neat demo, but what could you use this for? Did we talk about this? What would you use this for? Sport courts? How come? You just want it to bounce better? Yeah. So actually, bouncing is the reason they do this, right? And the application that I know of that exists, although I think it's illegal to use in some cases, is golf clubs, right? So if I'm not a golfer, but like apparently you want to hit this ball as far as you can, right? And so imagine what's happening. You got your golf club and you're swinging it as hard as you can and you're smacking the ball, and then some of that energy is denting your club. Well, what if instead of that, it just bounces further, right? So you can actually make apparently tremendously good golf clubs. Companies out there, they're called liquid metal. They don't make liquid metals. It's just amorphous metals. But imagine there's lots and lots of other applications. What if you just don't want something to scratch very easily, right? An amorphous metal is much more corrosion and scratch resistant, right? Anyway, so that's amorphous metals. The other thing that we're going to talk about more specifically today is a fuel cell car, right? Now, this is like a toy fuel cell car. What goes into this is on this back side, you can pop this thing open. And inside of it, you've got a chamber where you put, you fill the bottom of this with water, okay? This is just a plastic container. And then it's got these little hoses that go through the cell and then back into these gas chambers. So what you do is you start out by running this electrically. You provide an electric current, and what happens is electrolysis of water. Right? Electrolysis is splitting water into hydrogen and oxygen, right? That happens because inside here in this middle piece, which is, the size like an inch squared, is a fuel cell, right? We'll describe what fuel cells are in today's class. Anyways, water goes in on one side, it splits it pulls an electron from the hydrogen, making it H+. It takes and gives those electrons to the oxygens, making them 2-, right? And now you have hydrogen and oxygen separated. And then when you want to run this car, you disconnect the electricity, but now you have this reservoir of gases that you've created, and they're going to recombine to form water. They're going to give off electrons, which are used to power a small little DC motor here, and you get an electric vehicle, right? And this is a toy car, but the real ones exist, right? So if you look, you can look this up right now. Like you could buy it today. The Toyota Mirai is a not terrible looking car that gets pretty remarkable gas mileage, 66, right? It costs a lot, 60 grand, but I don't know, nowadays you buy big trucks for 80 grand, right? I mean, Tesla Model 6s are what, probably 60K or thereabouts, or Model S's, I mean. So, I mean, it's not like it's a crazy price, but it's not the most economic price either. One of the great advantages to these over electric vehicles, which I'm a big fan of electric vehicles, but these have some advantages over them. The biggest one is that when you run out of gas, there is no gas in here, there's hydrogen, right? So you pull up to a tank, right, a hydrogen tank, you refill and you're on your way in about the same amount of time as it would take to fill up gasoline in your car, possibly faster, right? So that's a big advantage. One of the disadvantages is what? What's the disadvantage to hydrogen cars? Distribution. Sometimes people say like, oh, these things explode, but like they've kind of got the exploding problem figured out, right? Even if you crash one of these things, a friend of mine works at Volute, a company that makes the gas tanks for these, and they've actually tried to make these things explode catastrophically, and it's hard to do. They use a carbon fiber serpentine coil, so it looks like your intestines, right? They hold the gas in something that looks like your intestines, but made of carbon fiber, and they've pretty well engineered this, so it's actually hard for it to explode. It's much, much more dangerous to crash a gasoline vehicle rather than a hydrogen vehicle. In any case, somebody up here said it, it's distribution. The problem with the Toyota Mirai is that if you buy it here in Salt Lake City, I don't know where you fill it up with hydrogen, right? And there might be a place, I don't know of it. So there's niche places in the Bay Area, in LA, in New York City. There's sort of these beachheads where they've established fill-up stations. But for the rest of us, it's not the most amazing option yet because of infrastructure, right? So hydrogen is not just important for vehicles, right? It's very important for energy, right? A couple months ago, this was in August, right? Fuel cells have been around since the 70s, but they're making a pretty big comeback. One of the biggest companies in the energy sector did a big IPO. It was like a $250 million IPO. It's a big public offering. And essentially, they're banking on these for renewable energy storage. So let's say we all believe in renewable energy. The big question is, what do you do to provide energy to people who need it when the sun's not shining or when the wind's not blowing, right? These are the challenges that we face in renewable energy. You have to have a way to store it. And the cheapest way to store it is what? What's the cheapest way to store energy? Anybody? It's surprising what they do. It's pumped hydro. You take a reservoir of water and you pump it up to a higher reservoir with the electricity you're generating, right, from solar or whatever. And then when you want to get that energy back, you run it back down through the hydroelectric mill, right? You can do that on a small scale, like a water tank in a small town. Or if you live by a mountainous area and you got a dam up in the mountains, you can pump it up into the reservoir up in the mountains. That is the cheapest way to store electricity, right? Currently, is pumped hydro. But that only works if you have a place where you can store lots of water, right? And that's not the easy, plus it has its own challenges with it. So if you don't want to do that, one of the most promising areas that's coming online is fuel cells. There's batteries, you can put it in batteries, or you could do fuel cells. And a fuel cell, just like I showed you, you could take electricity, right, just like this car did, like a 9-volt battery or a little solar panel that it comes with. You could take that energy and you could split water into those two gases and then recombine them at your leisure, whenever you want, right? That's the idea behind these. So fuel cells, the whole point of explaining this is that they would not function if it weren't for imperfections in a material. A perfect material where every atom's in its place, where it's a perfect alloy, right? All just a certain type of atom, they would not function. And we're going to describe today why. Why is that the case? Okay? And by the way, fuel cells look something like this. Like this is a stack. I don't know what power this is. This is probably like, I don't know what power this is. But they're layers of ceramic membranes. They don't have to be ceramic. There's polymer ones too. That are put together, and you essentially have like your air in and your fuel gas coming out, and then this would be hooked up to electrical leads and you generate your power. So they're small. These things aren't gigantic. They're pretty small. And there's advantages and disadvantages to the fuel cells. We won't get into them in this class because it's not specifically on energy. But I think it's a technology you should be broadly aware of. Okay? All right. So let's dive into today. We will talk about the things we talked about last time, the same objectives because we didn't get very far. And if possible, we're also going to move into one-dimensional defects. So we're not just going to talk about 0D point defects. We're going to talk about one-dimensional defects in materials, okay? And we'll see how much further we get. So we talked about the driving force for vacancy formation and the one preventing it. We said entropy is typically driving it, and enthalpy, or breaking these bonds, is preventing it. Actually, Avery, I'm sorry, I forgot. Do you want to talk about the Benyon Center? Or you want to wait to the end of class? Stop me when we got 5 minutes to the end of class, okay? So vacancies, how do we know how many there are in a given material? We use our old friend, the Arrhenius equation. Remember, the Arrhenius equation is when any property of interest, like NV, the number of vacancies at equilibrium, if it depends on something where there's an exponential with an activation energy, in this case Q sub V, that's the activation energy for vacancy formation, divided by the thermal energy, kBT, Boltzmann constant times temperature, that's an Arrhenius type of equation. So we can figure out the number of vacancies at any temperature if you know the following. N, that's the total number of sites, right? So in a crystal lattice, right? Let's say FCC for a minute. In FCC, you've got these atoms, right? That's on the corners. Then you've got front, back, top, bottom, left, right. So you can figure out what the site density is. That means how many sites are there per volume. And we know that there's 4 sites, right? Because there's 4 atoms in this crystal structure. There's 4 atom sites per some volume, right? So that would be N. That's your site density. And then N sub V, we calculate once we know the activation energy for vacancy formation. So let's go ahead and do a quick example of this. This will be our first clicker question. We're going to do it for copper. Copper has a vacancy formation energy, or an activation energy for vacancies, of 1 electron volt. So I want you to tell me what would be the vacancy concentration. Concentration is going to be NV divided by N. So you're just going to bring N over to the left-hand side of the equation at 800 Kelvin. So give that a shot. We're going to pull it up on Top Hat. And K right there, your Boltzmann constant in electron volts is what you want. That's going to make this a more convenient calculation. Since the activation energy is given in electron volts, not kilojoules per mole or something, there's KB with electron volts per atom per degree K. Okay, we'll do one more minute. What's up? Tell me one of those works.
You're searching for NV over N, right?
Yeah,
NV over N is what you want. So all you got to do is plug in the exponential.
I plugged it in, but it's not one of the answers.
like
Oh gosh.
the same magnitude.
That's okay.
The same.
Well, so I don't know if I'm being told that the answer that people are getting is not one of these ones. Pick the one that's closest to it. the right order of magnitude. I'll double check my calculation. Maybe I messed up on this, but okay, we're going to wrap this up pretty quick here. What's that? Yeah, I'll double check after class. Okay, we're going to close the poll. Okay, and people think this should be, oh, interesting. All right, I will find out what went wrong. I'll probably give you credit for either of those because I don't think that it was bang on one of those numbers. So how do you do this, though? It's a straightforward calculation. Let's do it together. NV over N is equal to the exponential of 1 electron volt. That's negative 1 electron volt because it's negative Q, right? Negative Q divided by, this is 8.62. I wonder if that's the actual value. I wonder if it's a rounding issue. But anyways, that's times 10 to the negative 5. That's EV per K. And this is all happening at 800 K. So when I plug those in, I get I get 5 e to the negative 7. Anybody else get that? 5 e to the negative 7. And again, so what would the units of that be? What would the units of this be? So it's the equilibrium number of vacancies divided by the number of sites. So that has no units, right? This would be like saying percentage, right? You could put this in parts per million if you wanted. You could, but it's a fraction right now, okay? Any questions on this type of problem? Yeah.
So NV over N is vacancy concentration. We're trying to solve for NV.
So I guess I asked for vacancy concentration, right? So yeah, technically, if I said what's the vacancy concentration, like the number per volume, then I'd have to tell you things like what's the lattice parameter, because in that case, and you're going to have a homework question on that. By the way, quick announcement on that. The homework is posted. Let me pull this up real quick. The homework is posted, but I had to change one thing. So if you downloaded it like the second that I posted it, make sure that you got the right copy. Problem 2 should have parts A through E. If it doesn't, then you downloaded it too quickly. But on the homework, you're going to have an example where you have to figure out the number of vacancies per volume. And in that case, you need to figure out NV, right, the number of sites. And then you need to figure out how many sites there are per volume. That's how you'd get the number of vacancies per volume. Okay, so you have an example to do that on a homework. And I think I've got YouTube videos where I've worked through that as well, solution videos. This is probably one right here. Yeah. So here's an example where you can go through the same sort of calculation, okay? Okay, any questions on this? On vacancy formation? So if you compared two materials and all things equal, if they've got the same number of sites per volume, let's say they're both FCC, they're both similar lattice parameters, but one has a gigantic activation energy and one has a really small one, you know the one that has the small activation energy is going to have way more vacancies than the one that has the really big activation energy, okay? All right, so how much are we actually talking about? How many vacancies can we even get in materials, right? So take metals. Even at their melting temperature, where you've heated it up about as much as you can heat it up, right where you're right there before it becomes a liquid, and vacancies don't really have the same meaning anymore, even at that point, most metals have NV divided by N of about 1 e to the negative 4, which means you have about 1 vacancy for every 10,000 lattices. So these things are not like everywhere, typically, right? The vast majority of compounds they're not like riddled with vacancies. They're pretty rare, but even at the 1 e to the negative 4 amount, they can dominate properties. They can really influence properties. Some of those we haven't talked about in this class yet, like electronic properties. They are very important too, like how electrons travel through a material. They can be dominated by vacancies, right? And that's going to be the case in fuel cells, okay? Okay, there's other types of defects we can have. There's vacancies, and then there's self-interstitials is the other one, point defect we'll talk about. So a self-interstitial, let's say you had an atom like this gray one at point number 2 here, right? You can see that you have a lattice of gray atoms, but here somebody's crammed in an extra lattice, atom number 2, which we call gray atom, which they call point 2 on this, okay? That's an example of a self-interstitial. Generally speaking, is this my next clicker question? Oh, right here, yeah. Would vacancy or self-interstitials have a larger energy penalty, right? So it's our next clicker question. If you read the text, you should know this. Which one of these comes with a larger energy penalty? Is it the vacancy or is it the self-interstitial? And if you're struggling on this one and you're not sure, ask yourself, which would be a more awkward situation? If you had a bunch of people lined up nicely and you took one out, or you put in like an elephant in the room? Like, which one's more awkward? Okay, we're going to close the poll. Okay, good. Man, this is just always the case. It's always like 15% of people are getting these wrong. I'm sorry. But interstitials cost more. They have a larger energy penalty. And the reason why is because they strain the surrounding lattice a little bit more. If you look at this, if you zoom in on that, it's not just the one spot that's messed up, but the nearest neighbors. Look at these. Like these nearest neighbors, they're also pushed out of position and so forth. Like it has this ripple effect on the surrounding atoms, which is going to compress bonds that don't want to be compressed, right? In general, compressing things, if we go back to our potential energy well, which we will go back to over and over and over in this class, as you separate atoms, they have their equilibrium distance, And then they tend to be steeper on this side. That tends to be a little bit sharper and a little bit less steep over here. So if you're squeezing things together, you pay a big energy penalty for it. So when you have a vacancy, they expand a little bit, right? Look up here at point number 1. In that case, the atoms are sort of pushed out a little bit from their normal position, but that is less steep, right? It's less of an energy penalty. In general, cramming something into a lattice is much higher energy penalty, okay? But that's self-interstitials, right? So again, self-interstitial means you have a copper lattice, and the extra copper atom that's out of place is a copper atom, right? It doesn't have to be the case that it's a self-interstitial. You can have other things. You can have dopants. Let's say you have a copper lattice and you put a nickel atom in it. We know that there's a solid solubility all the way across from copper to nickel, but they're not the same size. They don't have exactly the same chemical characteristics, and so there will be a chemical penalty whether it substitutes, meaning it sits on the site, or it goes interstitially, right? All right. So let's talk about point defects in ceramics. In metals, it was straightforward. You have vacancies or you have self-interstitials, are about all you have. In ceramics, it's harder for the same reason that crystal structures were harder, because there's different sizes and there's different charges on them. That leads to the same problems here with point defects, right? The different charges and sizes leads to defect structures forming, right? And there's two important ones we have to know about. There's Frenkel defect, named after Yakov Frenkel, a Soviet in the 20s, and Schottky defect, named after Walter Schottky, a German in the 20s, right? So here's the difference. A Frenkel defect is when you take, let's see, which one's which down here? Let's show you. A Frenkel defect is when you take it out of its normal site, like this empty spot here, that should be a red atom, but it's missing. This one should be a red atom, but it's missing, right? Those red atoms are located elsewhere in the structure, right? You see that? Like, so they come in pairs. This thing left, and now it lives somewhere else. So it's a pair. You have both a vacancy and an interstitial. That's called a Frenkel defect. A Schottky defect is different. A Schottky defect is like this one. You have two vacancies, one of each type. So in this case, it was a red atom that was missing, but that red atom was just located somewhere else. In a Schottky defect, you're missing a red atom and you're missing a green atom. So use whatever mnemonic device you have to come up with. Here's mine. Frenkel sounds kind of like a creepy name. Sorry to the Franks in the room. But like, Frank sounds like a guy who doesn't respect your personal space, right? Like, come on, Frank. Like, he's not respecting personal space over here, right? But Schottky, like, I don't know, it's like he shot a hole through it. They're both just missing, so that's what I use. Remember it however you will. But those are the two most common types of defects in ceramics. There's tons of others, right? And these are for pure materials right now. We haven't even doped these yet, right? This is just like, say, it's sodium chloride. These are defects that can exist in the pure NaCl. What happens if we start doping sodium chloride with something else? We put a little bit of like calcium, which is now 2+, right? What's that going to do? Sodium is 1+. You put in a 2+ ion, you're no longer balanced you don't have what's called a balance in electroneutrality. That's a problem. We're going to show you what happens in that case, right? First, let's ask this question, if we take an atom from the center of a material and I move it to the surface, is there an energy penalty? So imagine the students in this room. If this like block of students was totally filled and I pull a student out of the middle and I put a new chair on the surface, right, on this front row here, and I say, come sit right here, is there any difference, right? Yes or no? What do we think? I think this is our next question. Okay, is there an energy penalty, yay or nay? If you pull it out of the center and you have it migrate to the surface, is there a penalty we pay for that? Okay, get your answers in. We're going to close poll. Okay, what do we think? Yay or nay to an energy penalty? People think, again, always 80-20 basically of people that get it right and wrong. Yeah, there is an energy penalty, right? Now, why is there, right? Or an energy difference. For one thing, we've increased the disorder, right? For sure we've increased the disorder. So entropy, that's going to change it. But also, if we pull out somebody in the middle and they have like 4 bonds around them, and we move them to a surface, now maybe it's only bonded to Hector, right? It's only got 1 bond, and it wants to have 4 bonds. So we broke 4 bonds, we only made 1. So there is definitely a difference in energy when you move something from the center of a material to the edge, right? And then it depends, like, well, where does it sit on the surface, right? Because you can have a blank slate where it just sits right here in the middle of nowhere, That has some energy. But what if there's a ledge of atoms and it sits next or on that ledge? Or what if there's a kink in that ledge and it fits in that kink? Each one of those scenarios is going to make a different number of bonds, right? This one sitting right here is going to have like 1 bond below it. This one that sits here, the next one that goes there will have 1, 2, 3, the one below it, right? In that kink, it'll be maybe 4, right? So there's different energies for sitting in different spots. And because of that, when atoms do sort of grow on the surface of a material, let's say that you were sputtering this with atoms, which is something they can do. They basically, from the gas phase, they bombard this with atoms. They then get to choose where they sit. They could choose to sit right here in the middle of nowhere, but that costs more energy. So instead, they basically fill up these rows first and they sort of grow outwards, and then it goes and it starts a new one. And you can see this because we live in the future. We have microscopes that let us see atoms doing this. Should we do it? Let's do it. This feels right. AFM video step growth. Let's see if that pulls it up. All right. Hopefully YouTube doesn't let us down. Yeah, you see that? See how they're growing from one side to the other? We'll see another one come. It happened quickly. Here's another one. See that? How it's propagating? So this is an AFM image. AFM, at the end of this chapter, we'll talk about microscopy techniques. AFM is one of them. It basically, I'll get to it later. It's a video that shows the surface. I'll tell you how it works at the end of this chapter. I'm not going to get out of order. But you can sort of see that happen because there's an energy difference on where these things sit. Okay? We're going to skip this math for the sake of time. Sorry, math. It basically just describes where this comes from. So if you want to know, it's there. Okay. Now, when we dope things, right? What happens when we dope things, or if we have non-stoichiometric compounds? We've been talking about this a couple times over the semester. Our old friend Woostite, FeO, we said Woostite is a problem because it gives us both Fe2+ and Fe3+. By the way, this is named after the founder of the MPI. That's like Germany's version of the national labs. That was this guy. So, Fritz Wust. I don't mind naming a chemical after you. That's a pretty good deal, right? So you've got these two different oxidation states, but oxygen's always 2-. So if you have pure Fe2+, then it's going to be a 1-to-1 compound. But we've talked about if it's both of those, it's going to be something other than 1-to-1. You can have a non-stoichiometric compound, right? So that would be a different type of defect that conforms, right? Because in that case, the vacancy on the iron site is compensated by the number of Fe2+ to Fe3+, right? You've got Fe2+ and you've got Fe3+ ions. And depending on that ratio, you will create iron vacancies. They'll call these cation vacancies as opposed to anion vacancies, okay? Now, something that's really interesting is that vacancies, even though there's not very many of them, they can influence properties. We already said that they can influence electrical properties. They can also influence things like thermal expansion, and here's how, right? So let's consider the following plot. Let's say that you could plot percent change as you heat something up. So going to high temperatures. So I'm going to show two curves. First off is your overall curve, right? This guy right here, this would be delta L over L, right? That's L final minus L initial divided by L initial. That is delta L over L, okay? So if you heat something up, it's going to expand. And let's say that it's a linear material. They don't have to be linear, but this one, let's assume it's linear, right? So it starts out, it's 0, and it goes up. There's part of that is due to what we've already talked about in this class, which was what? What causes thermal expansion? Think way back to the very first chapter. To our old friend, the potential energy well. There's a reason we covered this first, because it just keeps coming back. When you heat something up, you're giving it energy, and the average position is no longer right here, right? The average position between here at this energy is maybe located slightly over, and so it's expanding, right? So the interatomic distances, the bond distances, are getting a little bit longer. And in other words, another way to say this is that the lattice parameter is increasing, okay? So if we were to draw a line that represents the lattice parameter change, it might do something like that, right? This would be delta A over A. So this is A final minus A initial divided by A initial, okay? That's our lattice parameter. So the key thing I'm telling you here is that lattice parameter alone can't explain the total change in length. There's an extra amount, right? And that's coming from vacancies. This is shocking. Like, think of what I'm telling you. If this room was totally packed, let's imagine all these students crammed into the smallest number of seats possible, and then I heat them up, right? And they're hot, so they like want to get away from their neighbors, so they start spreading out a little bit. It's going to expand a little bit, but in addition, the people in the very middle, some of them, a small fraction of them anyways, are going to get up and say, I'm sick of this middle business. I'm going to move to the surface, right? And if enough of them do that, by moving to the surface, you made the overall thing a little bit bigger, right? And it's big enough, you can actually see it with measurements, right? You guys don't look shocked. That's shocking, right? We're talking like 1 in 10,000 atoms is your vacancies, and yet it's enough to make significant changes on, like if you have like a ruler on a material, you can see it getting bigger. And a fraction of that comes from vacancies, right? So this difference here between the two curves, this difference right there, at any given temperature, the difference, that's going to be equal to NV divided by N divided by 3, right? It's our vacancy concentration divided by 3. Okay? Yeah, question, Sam?
I'm just a little bit confused about how the vacancies happen, I guess. Did you say they just like get up and move, but like how does that work?
Great question. How would it happen? So if it's like way deep within the middle of the material, how did that thing get all the way to the surface? It's a hopping mechanism, okay? So let's say that there's an empty seat, right? Right here, we've got an empty seat, right? So if don't tell me, it starts with an A, Harley, if he wants to get to the front, what really happens is like, it's a series, so all atoms are indistinguishable, right? So that exact atom doesn't have to get to the front. We just need an empty spot there. So if I was sitting here, right? There's an empty seat here. I could hop to here, and now there's an empty seat. Somebody else, like Harley, could hop to there, to the empty seat, right? And next thing you know, the vacancy is all the way in the middle. So it hops from the surface inward. That's kind of how it works, okay? There's other ways it can happen. It can go along grain boundaries. We're going to talk about this in the next chapter in diffusion, right? This is the lattice where everything's sort of ordered. But what about this region in between? So if I have the choice to move through the material, I could try and like climb over people, but that's going to strain them and cost energy. Or I can like walk down the aisle, right? So like diffusion grain boundaries are diffusion short circuit pathways. Things can move much quicker along grain boundaries and other things, which we'll talk about later. Okay, any other questions on this? On how thermal expansion is the blue. That's what you measure, right? If you had like a ruler or a calipers and you measured the length of something as you heat it up, you're measuring the blue line. X-ray diffraction or other tools can give you the red line. And I'm telling you that there's a difference between that, and that difference is the vacancy concentration. Okay? So there's an expression on the homework. You're going to use this. So hang on to that in your back pocket. There's a homework question on it. Okay, we've talked about pure metals versus now doped materials. We've said that, oftentimes pure metals or materials aren't even what we want. Sometimes they are, right? If you're making integrated circuits for computers and things like that, they want incredibly pure silicon. In fact, you might not know this, but like places like Intel and them, what does silicon come from? It comes from sand. They start from SiO2, and they don't even get it from just anywhere. They buy it from like specific sand dunes in the world that are like high purity, because it's just too hard to refine out. So they actually get their quartz not from like Long Beach, but from like specific spots in the world with high purity sand. And they can get it to what's called 99 purity. That means it's 99.99999 and so forth until you have 9 nines purity. What that means is, I used to have it. I think that's like 1 in a billion atoms are not silicon. So incredibly pure, okay? It's very hard to do that. It's hard to even get what's called 6-9, and you pay for it. If you guys go out and work in industry and you naively think, oh, my boss wants me to make whatever compound, I'm just going to order really pure materials because that seems like the thing to do. They cost crazy amounts of money, right? 5 or 6-9 pure, like, Logan, what does it cost to buy that? To buy even cheap stuff like iron at 9.9 purity will cost you a couple $100 for maybe 100 grams. Right? Very expensive. And if it's at all, and that's for a common material. Then if you want ultra pure something like scandium, right, which is rare to start with, forget it. It's just crazy expensive. So that's purity. We don't have time to talk about how you purify things, but impurities often get left over, and sometimes they get left over by design, right? So alloys are things where it's left over by design. Sterling silver, you've heard of sterling silver. That is 92% silver, and then the rest is copper. The reason they do that, for one thing, copper's cheaper, right? But the real reason they do it is because adding copper changes the properties that you care about, namely the hardness and the yield strength. It makes it more scratch resistant, and we will talk about why in a few chapters. But adding a little bit of copper, even though it's a substitutional alloy, it substitutes for silver, it makes it harder and therefore it's scratch resistant, which you want if you're going to make it jewelry, okay? But there's stainless steel, we've already talked about that. You take out some of the iron, you put in at least 12% chromium. Now you've got this nice oxide layer that forms because the chromium oxidizes and protects it. You've got pewter, brass, bronze. All these things are mixtures. They're intentional mixtures of metals that have some exact property, like Muntz metal. They use this to make it's corrosion resistant in salt water, right? Just like the one above it. Both of those things are pretty corrosion resistant in salt water. Solder we've talked about. So there's lots and lots of alloys that you should be aware of that they're not pure elements, but they're intentionally solid solutions. Okay. Okay. How do you know where an atom's going to go? We've already said that if I've got a dopant atom, if let's say all the students in this room are copper, and I've got a nickel atom, and I say, I'm going to mix it in with that, where's it going to go? Is it going to ask Elias to get up and move and sit somewhere else and take his seat, which is a possibility? That's a substitution. A substitutional thing, or is it going to be interstitial, right? If he sits next to our sleeping friend here, then that's an interstitial, right? He's like going to be crowding, and he's awake, right? So you have the option substitution or interstitial. How do you know which one it's going to be? So there's some general rules. Here's our rules. If it's the same size, it's more likely to substitute. If one is larger than the other, the larger ion will substitute, right? So again, let's say you've got like the Kool-Aid man, and the Kool-Aid man wants to take a seat. If he tries to sit in an interstitial, that's not going to work. He's more likely to like kick someone out of their seat because he's already too big to start with, right? Lower charge ions tend to be substitutional. That's really the same reason as before. Lower charge ions are bigger ions, so they tend to substitute. We get substitution if you get the same crystal structure and if there's not a big difference in electronegativity. If it's not the case for any of those four rules, then you're likely to get interstitial, okay? All right, let's get to the most interesting thing when it comes to these dopants, is what do we do if it's a different charge, right? Let's take yttrium 3+, right? That's our ion, and we're going to substitute it in to zirconia, right? Zirconia, ZrO2, in that structure, it's Zr4+, right? Because there's two oxygens, so you have to have 4 positive charge to have this thing balance out. So what happens if I pull a zirconium out and I put an yttrium in? It's not balanced. And we've said that electron neutrality has to be conserved. So what will happen? Maybe turn to a neighbor. What will happen if we put in an yttrium on a zirconium site? And the picture kind of gives it away, right? You're going to have oxygen vacancies, right? So by putting in a 3+ on a 4+ site, you don't have enough positive charge. So you could either try and add extra positive charge, but that's going to mean putting extra yttrium like in interstitial spots. Interstitial spots cost a lot of energy, right? That's cramming extra atoms in. That's less likely. The other option you have is forming oxygen vacancies, because if you take out an oxygen, they have a negative charge. So you could, by having this yttrium, which doesn't make it positive enough, if you pull out some of your negative, you can make it work. So how many do you have? For every 1 yttrium substitution, you are deficient in your positive charge by 1, right? 3+ on a 4+ site, you're deficient by 1. But oxygens come in a charge of 2. So what you have to have is for every 2 yttrium, right? For every 2 yttrium that you substitute, you have 1 oxygen vacancy. That makes sense? 2 yttriums, now you have built up a positive 2 that's missing. So you make up for that by pulling out a negative 2 ion. Make sense? Are there any questions? Yeah.
So is it more energy favorable to do that other than just say replacing oxygen with chlorine?
So yeah, you can have, what do they call these? Co-doped samples. Co-doped samples is one's exactly what you're getting at. You dope one thing, but you also dope the other, and then you're left with no vacancies afterwards. It's going to depend system by system and dopant by dopant. If that's more favorable than forming vacancies, it totally depends. In general, vacancies don't cost that much, but interstitials, putting something else on there, tend to cost a little bit more. They tend to be much less likely because the size of ions is rarely the same, and so there's usually crowding of some sort. Okay? So why do we care about this? So this is what happens. This is amazing, right? Remember the same zirconia that was amazing because it's kind of like steel and that it's tough? Remember how that worked? We said that you doped it with something. You dope it with yttria, just like this. And what we said happened there was that at high temperatures, there's a phase that is kept in a metastable state at room temperature. And then when a crack comes nearby, that phase expands and it closes the crack. Right? So a completely unrelated phenomenon in the same material is this. Now we've got oxygen vacancies, but it makes it incredibly important for a different reason. If you have oxygen vacancies, that's like having empty seats in this middle block of students, right? If there's empty seats and somebody wants to slowly like hop their way to the back of the room, you have a pathway for that to happen. If every seat was filled, then you're like climbing over people, and that's not ideal. But if there's empty seats and you can hop, like that's pretty good. That's a pretty good thing, right? So that's what happens here. You make sensors out of these, right? So this is in every single vehicle ever, right? Well, new vehicles. Old vehicles didn't have it, right? But new vehicles all have fuel injection, or they have at least an oxygen sensor, right? How it works is you've got this sticking into your exhaust pipe, right? So you've got the effluent coming out of your motor, and if you've tuned your car motor correctly, then you have the precise ratio of oxygen to fuel such that it burns and you're not left with any excess unburnt fuel, right? Soot, which is not good for anything, right? You want to burn all of that so you consume the correct ratio. But the problem is that ratio needs to be tuned as temperature and altitude and all these other conditions change slightly. So what you need is a way in real time to figure out how much, let's see, which side's which? This is ambient air, this is sample gas. So inside your catalytic converter, inside your effluent gas, you need to figure out how much oxygen is there. If there's way too much oxygen, then you're not adding enough fuel. If there's not enough oxygen, then you don't have enough air to it, right? And so you need to be able to tune that. So they embed these things here, and how it works is amazing that it works like this. In air, you've got 21% oxygen, and if you have no oxygen here, there's a gradient in the concentration, right? Therefore, there's a driving force. We're going to learn about this next chapter. But there's a driving force to move from here to this side, only if it conducts ions, right? Because it's a solid material. Like, it's not like the gas can diffuse through it. It's completely solid. Gas, it's airtight, right? So the only way that molecules can go through it, gas molecules can go through it, is if they turn into an ion, an O2 minus ion, and they start hopping through this lattice, and then they arrive on this side. And then all you have to do is you line this with a conductor, like they use platinum, right? And then you measure the voltage across that difference, and there's a very simple expression that tells you what the voltage is, how it relates to the oxygen pressure on this side of your tank. So in real time, you can measure the voltage almost instantly, and it will give you an instantaneous measure of how much oxygen is in your effluent. So in real time, this is why EFI Live, electronic fuel injection live, this is a system that in real time will change the mixture of fuel to air in your engine, so you get the most power, the most fuel efficiency, and the least pollution. And this is made possible by our friend aliovalent substitution, right? A substitution of atoms with a different charge that creates vacancies. This is amazing. This is the exact same thing that allows fuel cells to operate, right? Fuel cell, this is also YSZ. YSZ, yttria stabilized zirconia. That's yttria doped into zirconia. You want to be able to transport oxygen from the air. You want it to travel through the membrane and end up pure oxygen on the other side. This is what allows you to separate that, because only oxygen ions can travel through these membranes. Hydrogen cannot, right? Or you can build these opposite. You can build them with a hydrogen conductor. Those are polymers. And then the oxygen can't get through, but hydrogen can. You get the same end result with a totally different setup, okay? Are there any questions about this on the role of dopants and how they create these sort of really important defects in a material? No questions? Okay, let's keep going then. We got just enough time for Avery to tell us about the Benyon Center. We got 3 minutes. Go ahead.